In one of my previous videos, I did a teardown of a cheap eBay-bought electromagnetic radiation tester, which claimed to be able to detect electromagnetic fields. And in my testing, you saw that while it was able to detect the presence of electromagnetic fields, it was not able to accurately quantify the field strength at all, and the readings were pretty much meaningless. So it was more of a toy than a piece of scientific instrument. Today though, I have a professional-grade magnetometer here on my workbench. Of course, this is a used unit from the early 90s. It is a MEDA PLM-100 AC magnetometer, which is capable of measuring the presence of very minute alternating magnetic fields with two ranges, a 20 milligauss or 2 microtesla range and a 200 milligauss or 20 microtesla range. MEDA is actually a short for McIntyre Electronic Design Associates, which specializes in space and laboratory-grade magnetometer manufacturing. While I do not have the detailed specification for the PLM-100 series, according to the literature available, which I will provide the link on my website, the reading accuracy of this instrument is within 1% traceable to NIST and with a precision and resolution to 0.1 milligauss or 1 nanotesla. AC magnetometers usually are very simple in terms of operating principle. The core usually consists of an induction sensor, aka a pickup coil, and a transimpedance amplifier, which converts the alternating current induced in the coil into an AC voltage signal. Now let me quickly illustrate how this works. In its simplest form, a transimpedance amplifier works something like this. So here we have an op-amp, and we have the input and the inverse input. So the input is tied to the ground, and the inverse input is our current input. So here we have the I-in, input into the inverse input here, and then we have the V out. And here between the output and the inverse input, we have a feedback resistor, RF. And this forms our basic transimpedance amplifier. And how it works? Well, when we take a look at an ideal amplifier, we can see that between the input and inverse input, there's no voltage drop, and also there's no current flowing in. So all the current I-in flows through the RF to the output. And from the output perspective, the V output equals minus I-in times RF. So we now have this relationship, and of course we can calculate the impedance Z equals V out over I-in, which is negative RF. So basically, the transimpedance amplifier can turn a very, very minute input current signal into a relatively large output voltage signal. So where have we seen this op-amp configuration before? Well, this is how a feedback ammeter and the front end of an electrometer is usually configured as well. So basically, we can measure very small current with little or no voltage drop with this configuration. And here we have an ideal op-amp, so clearly you can see that the voltage drop here is 0. Now, of course, we will open up this magnetometer in just a little bit and take a look at exactly how it works inside. But just by looking at the sensor itself, I'm pretty sure that this magnetometer operates in the same principle as we just discussed here. In general, though, there are many types of circuits that can be used for detecting magnetic fields. For instance, we can use a Hall effect sensor to detect magnetic fields, and most smartphones nowadays already have a Hall effect sensors built in. Another one, a slightly more complex approach, is the so-called Fluxgate Magnetometer, which use alternating excitation voltage to drive a pair of highly permeable magnetic cores to saturation. And depending on the magnetic field's alignment, the induced current varies slightly between the positive half and the negative half of the cycle, and the difference then can be used to produce an output voltage which is proportional to the field strength. And before I proceed to the teardown, let's take a quick look at the performance of this PLM-100 magnetometer. Here I have the output from a signal generator, and it is sinusoidal output at roughly 60 Hz. My understanding is that this particular magnetometer was designed primarily for detecting mains frequency, and thus was most sensitive at around 60 Hz. And also it was probably designed for EMC or electromagnetic compatibility testing purpose. So let's take a quick measurement at the signal we have here. And for that I'm going to use my multimeter here. Let me just prop it up so you can see the readings. And I'm going to change to Hertz, the frequency measurement. And let's take a quick look. So the reading here is right around 60 Hz. And so let's take a look at the voltage. So the output voltage is at roughly 0.82 RMS. And so the actual voltage doesn't really matter. I just want to set it to a relatively low voltage so we can power some coils and see how sensitive this magnetometer is. And now let's turn on the magnetometer here, and I'm going to use the lowest range is 20 milligauss. And upon turning off, you can see that we have some reading, and I suspect this is from the environment. And so to test that theory, let me turn off the light to see if that is from the lab lighting. So let me turn it off. Yep. And as you can see, when we turn off the overhead light, this reading reset to 0, so that clearly was interfering with it. But let's keep that in mind. And unfortunately, this one, it's a pity it doesn't have a zero out functionality here, so we'll just have to keep that offset value in mind when we're doing further testing. And so for the experiment, I have two coils here, and these are just picked from my component drawer. One is a smaller one, which measures at about 10 millihenry. And the other one is a slightly larger one, which measures at about 100 millihenry. And the actual component values don't really matter that much. What I'm going to show you is that the strength of the field differs for between these two coils. So now let's take a look at the smaller one. For that, I'm going to place it at about 2 inches from the detector, and I'm going to hook up my signal source. So as you will see, that we get about 5 or 6 milligauss readings from the smaller coil. So let's now take a look at the field generated by this larger coil. And for comparison purpose, I'm going to put it relatively the same distance, about 2 inches from the detector here. And I'm going to run the signal through this coil. And of course, you will see that we get a much stronger reading. Of course, now this is slightly off a line, so I suspect if we move it up a little bit, we're going to get even stronger readings. And sure enough, we're now reading about the 16 milligauss instead of the 14 when we were down here. So clearly between these two coils, the larger one generates a stronger field, and that's to be expected. Especially given this two, I chose deliberately that the impedance of these two DC resistance are both around 50 ohms, so that the current flowing through are similar. And so basically it's primarily determined by the number of windings and of course the shape, all taken into consideration. They generate different magnetic fields, but nevertheless this one definitely is stronger. So now you get an idea of how sensitive this magnetometer really is. By the way, the signal generator's output is with an impedance of 50 ohms, whereas my coil has also an impedance of 50 ohms. So when we hook up these two together, I expect the voltage actually dropped by half. So let's just verify that before I put this away. So this is AC voltage, and we're measuring at, let's see, roughly 0.8 volts. So when I put on this coil, it'll drop to 0.4, yep. So that's a very, very small voltage across the coil. And we can see the effect on this magnetometer. Okay, now it's time for us to open it up and see what is inside. And with these self-tapping screws removed, we should be able to just open it up. So let's take a look at what is inside. Yep, and it opens quite easily. And here is what we have. So let me change the camera to a different angle, and we can take a look at it with greater details. Now we can see the inside of this magnetometer. There are actually not that many components inside, which shouldn't be a surprise. As we mentioned earlier, at the heart of an AC magnetometer like the one we have here is a transimpedance amplifier, which turns the induced current from the sensor coil into a voltage signal, and then the voltage signal can be used for further processing. Of course, the circuitry is slightly more complex than the single op-amp transimpedance circuit that I illustrated earlier for the demonstration of the operating principle for this type of transimpedance amplifier. In a practical circuit like the one we have here, you typically have some kind of frequency compensation for the input so that we can cover a relatively large range of frequencies coming in. And also, we might need to take care of linearity of the signal and so on and so forth. So here you can see that there are two wires coming in from the sensor. Although I can't see what the signal wires are connected to, I'm pretty sure that it eventually goes into this operational amplifier here. I will try to take out the whole PCB and take a look shortly. But now let's take a measurement at that coil to see at least what the resistance it has. So let me move in the meter here and put into O mode, and you can see here. So now let's take a quick measurement here. And it's at and it's at 100 ohm, give or take. So I just zoomed in a little bit so we can see the circuitry a little bit better. And here at the bottom, this chip is a op-amp, which is a TL32 JFET input op-amp, which is ideal for using as the op-amp inside this transimpedance amplifier due to its low input offset voltage and very low input bias current. Besides being a JFET op-amp, there's really nothing special about it, and in fact, it is a rather common general purpose op-amp that is readily available at a very low price point. And in the upper middle here, we can see an AD636, which is a true RMS to DC converter IC. The date code here says it's a 9116, so we can infer that this unit was made sometime back in 1991 or shortly thereafter. The AD636 is probably the most expensive component inside this unit. It sells for more than $20 a piece on DigiKey and Mouser. The true RMS converter chip is necessary as the measured AC magnetic fields are not guaranteed to be sinusoidal. And we have another TL032 at the back here. Not entirely sure what this one is doing, but from the traces, it's possibly interfacing with the AD636 in some fashion, I would imagine. And of course, we have quite a few trim pots here and there for fine-tuning the parameters such as linearity, amplification, so on and so forth. After all, the measurement is done entirely in the analog fashion. So now let me zoom back out. And so what I didn't see is any display circuitry. So presumably this display is self-contained. It's a 3.5 digit display. And from the trace seems to be supporting that. We have only 1, 2, 3, 4, 5 traces going into the display area. So let me take the board out, and hopefully we can also remove this display, and we will take a closer look at the PCB here. And I think if I'm correct, this display can be pulled out because I can see a standoff at the bottom. Now I don't want to break anything. I'm going to generally pry it. Yep. So now I can see that the thing pops right off. So indeed, this display is a self-contained unit, as we can see here. Even though we have many pins, I don't think that most of the pins are being used, because if you can see that the traces, we only have very few traces going into the display area. And of course, what I didn't show you is there are two jacks here, and the one is for RMS output, one is WB, not entirely sure what that is. And oh, that's wideband output. So presumably, now I'm thinking more about this, one of these TL083s, not 83s, 32s, is probably a filter of some sort, so that we can produce a wideband and narrowband output, depends on how much filtering we add to the circuitry. So that's probably what that is. And so it seems like we can remove these screws and we can take out the board. Of course, I'm not imagining going to be a huge surprise at the back, because I don't think there's anything at the back of the this board, but it's still interesting to see how it was made. And let me remove the battery here. I want to make sure that, yep, okay, so it actually comes out right pretty easily. So this is the board, and as you can see here, we have the two outputs for, so you can measure the signal directly from these two outputs. And here is our power switch. Oh, here are the... Very interestingly, if you look at this, is we have a section that seems like a protoboard area. I'm not entirely sure what this is for, but there's no component on either side, and so it's totally not being used. And you can see here from the data code again on the PCB, it says it's June 27th, 1991, so that was the presumably the manufacturer date. And so that's pretty much what this unit looks like. And as you can see, it doesn't have that many components inside, but the operating principle is quite elegant, and certainly this is magnitudes better in terms of performance than the cheap eBay bought electromagnetic field detector that I showed a couple of videos ago. And before I totally forget, let's also take a look at where this sensor, the leads coming in, is connected to. So we can see that this is ground. This black wire is connected to the ground here, and the signal in is this white wire. And here you can see that it connects to this resistor, and the resistor goes back. That's where we couldn't trace it before we took out the board. And it goes into this potentiometer and then pops out here. So this pin goes into this capacitor here, and the capacitor comes back here, goes into pin number 6, which is one of the input in the inverse input into this op amp, which is exactly what we said before. That's how the signal goes into this transimpedance amplifier. So I hope you enjoyed the video and learned something new. If you liked the video, please give it a big thumbs up and remember to subscribe, share, and I will catch up with you next time.